moving for this week, you're going to be looking at solving a lot of problems that are complex, but in a different form, because when you start doing more complicated problems, let's say like this problem, which we will eventually want to raise this to the 8th power, it's very difficult to do that by hand in the current format. So that would mean you'd have to use the box method or multiply it out, like this, and you'd have to do 8 of these, right? You'd have to do this 8 times and simplify everything 8 times without making a single mistake to figure out what -5 plus I to the 8th power is. It'd be very, very difficult to do that. So we have this other format that's called the trigonometric format, which is linked to the unit circle, which will become more of a geometry problem, which is really cool. That will help us solve these problems. You're also going to have to find like the cube root. Same thing. Find the cube root of complex numbers. Very difficult to do in this standard form, but when we convert it to this other format, which is based on the unit circle, it becomes a lot easier. So you're not going to see any of that till I think Wednesday. Just so you know, that's what we're leading up to, and that's why there's a need for this other format, this trigonometric form that we're going to use. Okay. So just a reminder, what we're dealing with is that we have these complex numbers. All right, complex numbers. All right, and those are comprised of 2 parts, the reals, right, and an imaginary part. Okay, so the reals, or the imaginaries, is this B part at the end, and of course the real number is the A part. Okay, so that's step 1. Just remember what a complex number is, right? And we can graph these just like we graph, pretty much anything else. So down here, let's go ahead and remind yourself how to graph this. So instead of an XY, even though it looks much like the graphing we've always done, it's not XY, it's actually AB, right? Where A is the real number, in this case 2. 1, 2, right? And then B would be -6, so it'll be down 6. 1, 2, 3, 4, 5, 6. So this complex number can be graphed right here. So that's the complex number 2 minus 6i. And it's not only just a point in space like on a Cartesian coordinate. This looks like 2, -6. With complex numbers, it's more of a vector. So we have this distance from the origin to the end of it, and we usually put a little arrow on there as well. So we treat it like a vector because it's kind of like a unit circle. You can imagine we can make a triangle out of this. We can find the theta. We can have an r. We can do all the normal things we would do with a unit circle problem, but we're going to be doing them with complex numbers instead. So that's the tie-in between all these and how they overlap. But even if you didn't learn this in Algebra 2 last year, or Advanced Algebra 2, Honors Algebra 2, like it basically mirrors, graphing coordinates. Okay, so go ahead and graph number 1. Draw your axes and keep it simple. All right. Calibrated, I think. There we go. This is off. Okay. So it should look just something like that. All right, so how do we bridge the gap between these complex numbers in this format, the standard form, and then into this trigonometric form with the unit circle in mind? So we've already kind of done this when we explained why in the unit circle, the x-coordinate is the same as cosine, and the y-coordinate is the same as sines. But it's worth repeating, so let's take a look at that. So just recall, if we have a, just look at first quadrant only. We have some triangle of some theta in quadrant 1, right? And we know that for this we need an angle and we need a radius, right? That's how all this stuff works. And with a unit circle, the radius is always 1. Not going to be the case moving forward. They can be 1, but usually it's not just 1. But when we did this, we said we use x and y here. Instead, we're going to use our a and our b, right? Because now it represents the a plus bi. So it's no longer just a xy coordinate. It's now in a complex number. But all the math is going to work basically the same. So when we proved that cosine was the same as x, all we did is say, well, cosine of theta, right? Cosine of theta is equal to adjacent over hypotenuse, a over r. And then we said the sine of theta was equal to the opposite over hypotenuse. Sine is opposite over hypotenuse, which is b over r. And when we were doing this in the unit circle, we just said, well, r equals 0. That's why x was the same as cosine. R was the same, b was the same as sine, or y was the same as sine. So, but this time r is going to stay there, so we're just going to multiply both sides by it. Right? Those cancel out. So we have, start with what we had already, a plus bi. And then from here, cosine theta, or r cosine theta, is what a equals. So we can substitute, right here, we can substitute a for r cosine theta. And that's a trigonometric representation of a. So any a value, the real value of any complex number, if you find the radius and find the cosine of the angle, find the angle, of course, first, and then take the cosine of it, that's the same thing. They're equal to one another. And on the other side, we just get over here, r sine theta equals b. This is r sine theta. Now we also have the I, right? So we have the I as well. On the standard form, the I is usually last. In the trigonometric form, we usually put it right in front of sine. So we say r I sine. That's how we say that. R times I sine theta. And then we can just factor out an r. So from here, just factor r out. So I can take r from here, and we write it with parentheses, since we factored it out. And then we get our trigonometric form, which is cosine theta plus I sine theta. And when we convert all our standard or complex numbers from this form to this form, and we start taking it to the 8th power, it's actually going to be a whole lot easier. Right, and you'll see that down the road, why. Okay. So this is the trigonometric form, this is the standard form, and today you're basically just practicing first convert standard to trigonometric. That's what these two are. Convert these to the trigonometric form, and then afterwards start off with trigonometric form and convert it back to standard. So you're just going back and forth and getting comfortable with the math, which is basically all unit circle. So if you know your unit circle, it's pretty quick. So starting here, so this is where your background knowledge is going to come in handy. So this is you want to look at this and say, well, -1/2 root 3 over 2. Where is this? What angle is it? And if you can get this answer quickly, that's going to make this whole week a lot faster. If you're kind of staring at this and we forgot the whole unit circle, that's going to slow you down. So you want to practice and practice and practice, so by midweek it kind of becomes instant again and really quick. All right. So keep in mind, don't memorize it. I would say don't memorize the unit circle. Right. That's the hard thing to do, because then it's easy to forget. But understand, these are all triangles. This is saying the rise is bigger than the run. Root 3 over 2 is a bigger number, right? So that's a 60-degree reference angle, because those are the taller angles. Right? When it has a 60-degree reference angle, that means they're taller triangles. So this is going to be a 60-degree, which means it's going to be over 3 in the second quadrant. So you can get 2 pi over 3 or 120 degrees. Right? Either one. Now, if you can do that, you're going to be in good shape. So the way to write these is in this format. So I found the theta. We're just going to put theta in for both of these. And keep in mind that both of these right here, these thetas, how there's two of them, there's one for cosine, one for sine, they have to be the same. Right? So we found 2 pi over 3, so that means both of these, it's going to be cosine 2 pi over 3. Right? And then plus I sine 2 pi over 3. So these thetas are the same angle. There's only one angle in each problem, so these two are always the same. All right, so that's the first thing. We have the angle. Now you need to know what's the radius. So what is the radius of this circle where this coordinate is found? What is it? 1. And how do you know that? It's on a unit circle. Perfect. So you got to remember, if the numbers you're starting off with are on that unit circle, if you look at the unit circle printout and you see these coordinates, that means the radius is 1. Now let's say you didn't know that. You kind of forgot. How do you find the radius manually? Okay? So you can say r squared equals a squared plus b squared. Right? Or x squared plus y squared. It's just Pythagorean theorem. So that would work as well. So we'd have -1/2, that's the real, plus root 3 over 2, that's the imaginary, and do the math. 1/4 plus 3/4. So r squared would be 1, and therefore r is equal to 1. So you can always solve for the radius manually if you kind of forgot or you're not quite sure. The angle, what if you kind of forget about the angle? Right? If you don't remember that, well, you could do rise over run. Right? If we plotted this out, we have this theta we're trying to find, and we have the rise, which is the b. We have the run. So rise over run, you can use arctangent, and you can get the angle. So that's another way of doing it. If you didn't know it off the unit circle, you could say, well, what's the arctangent of my rise, root 3 over 2, over my run, -1/2. Right? And that'll lead you to 2 pi over 3 as well, or 120 degrees. So our hope is that we don't, with the unit circle stuff, we don't have to manually write out the Pythagorean theorem. We don't have to manually put this, in a calculator or something, but we just recognize it quickly. Right? All right. So, also, like most things, if you have a multiple of 1 in an answer, you don't really need to put the 1 there. So we could just write this, the final answer, as this. And it's assumed that you understand if there's no parentheses or r in front, that it's 1. So you just have to understand that to be a thing, right? That without it being written, right, we know that this is a 1 here. But we don't have to write that in the answer. Okay. All right, try B. See how that goes. Draw it out. And make sure it makes sense. You can go through the steps, but it also should make sense. So negative 3i would be what? Down 1, 2, 3. So negative 3i would be right here. So what is the radius? How far is it from the origin to here? Just 3. Radius should be positive, right? So we do a squared plus b squared equals r squared, meaning it's always a positive number if you just add 2 squared numbers, right? So that should be positive. You know it's down 3. It's still a radius of 3. And then what is the angle? What is that angle? Radians? 3 pi over 2. Right off the unit circle, right? Now you could write it as the 270. That's fine. Just use the back of the book as a guide. I think in general we default to radians. So, but it's not necessarily wrong. We could even write this as negative 90 degrees and negative pi over 2. That's the thing as well. So the angles could be negative, but the radii we definitely want to keep positive. So again, it's all unit circle, right? You just have to know, if you remember this is 3 pi over 2, right? It's a very fast problem. If you kind of look at that and say, well, I forgot what the unit circle is and what they are, and it's going to take a while to kind of get used to it again. So just have that out, and it won't be too bad. All right, next, let's see here. We go to the other way. So we need to know our unit circle here as well. First thing, just substitute in what the cosines are. And these are generally on the unit circle for our purposes. So what is the cosine of 330 degrees? 11 pi over 6. What is the cosine? The run, right? What's the run? Root 3 over 2. What's the rise? Negative 1/2. Perfect, right? So if you can recall that quickly and like just off the top of your head, it's that easy, right? Otherwise, you have to maybe write it out. You say, okay, here's the circle. Okay, the run is longer than the rise, so I know it's the root 3 over 2. And remember that this is negative. That's important. Like all those little things, just like they were before, are still important now. And then you just finish by distributing. That's not bad, right? 2 times root 3 over 2, root 3. And 2 times negative 1/2, it's negative 1 with the I. And of course, once again, if you're multiplying by 1 in an answer, you can drop the 1. So we can just write this as root 3 minus I. So this is the standard form. This is the A plus BI format. All right, and this is the trig form that has the sine, the cosine, and I sine. Basically, it's like an X and a Y, but for complex, it's really not X and Y. It's A and B. Okay, so try number 3. Same idea. Okay. Not too bad, right? On all these, you could use the long way. So you'll notice sometimes on your homework, if you don't recognize the coordinates and they're not like easily, like I don't know where that is, where that would be on a, unit circle, you can use the arctangent and you can use the Pythagorean theorem to figure it out. So you will need these at some point. It's not all going to be unit circle, but for most of it, it will be. All right, you got plenty of time to probably get this whole thing done. Stay busy and ask questions if you got them.